Hello, welcome to Engineers Ireland and to the second talk on applied mathematics. Now, I hope the last talk was what you required. In other words, it was enough for you to be able to go through the questions in that section. If it wasn't, please email us. And first off, we'll learn from what you say, but secondly, if there are particular points that are a concern to you, we will address them. Today, what we're going to do is a natural follow-on from the last one. The last one covered motion in a continuous, in one line, in a straight line. What we look at now is motion in a curve. But again, it's going to be a constant acceleration problem. Either you will have velocity doesn't change, so acceleration is zero, or if there is an acceleration, it will linearly increase or linearly decrease. For these kind of problems, we actually have to have no atmosphere at all. Probably very appropriate when you think of all the maths that's in this. Fundamentally, if something is kicked, let's say if you kick a ball, we would say it looks like that. That's the way it runs. And it hits the ground over here. Now, that's symmetric. Around the middle, it's evenly distributed. It means the peak, the top of it, occurs halfway along. Now we can call it anything you like, okay? We will just call it range to half of the range. This overall length here is called the range. You'll notice that the guy kicking the ball is on level ground. To start off, to make life easy for you, we are picking, and the course picks, the easiest problems. There's no atmosphere in this condition here, so I hope this guy has come well prepared for it. It's probably the shape of the path of the golf ball that was hit on the moon. I don't know if you know it, but one of the guys brought up a golf club and golf ball, and he has the record for the longest golf hit. If there was atmosphere here, what you'd have is air resistance. And air resistance would mean that the faster the thing is going, the more resistance. You'll know it yourself from, for example, if you're cycling a bicycle, the faster you cycle, the more the wind pushes against you. And because it isn't evenly impacting the thing that's moving, it means that your acceleration won't be a constant one. So you can't solve those problems with ordinary algebra and trigonometry. For those type of ones, you need to use calculus. And the good news is, towards the end of the book, and it'll probably be only about 3 or 4 more chapters by the time I will actually get to this one, we'll be dealing with calculus, and you can see then how those problems are solved. At the moment, we are still trying to use our 3 basic equations of motion, the ones that are in the logbooks, and the important thing to remember is that they only apply when acceleration is constant. So, let's look at this. It's a curve. Curves are a problem because it's actually hard to think how you solve a problem with curves, but already in your mathematics you've learnt many times, and literally since second year, if not first year in secondary school, you've learnt that you never really solve a problem with a curve. What you do is you replace it with 2 smaller, simpler problems. If we look over here and we say that is the initial direction that the ball moved at. We'll assume it was a kicked ball. Now this could be a projectile from a gun. It could be any sort of thing. It could be a stone thrown or whatever it is. But if we look at that initial one, now we can call it, and the book calls it, u. And we can address it in 2 ways. We can either just do algebra, and then we're very much into using trigonometry, Or to begin with, to make life easy for ourselves, we'll talk in terms of vectors. So this u, because it's a vector, has both a magnitude and it has a direction. And like anything else, and you've been finding it in your maths courses, you can split it. Now, to begin with, and also to try and make it easy for you to get your head around dealing with problems where something is moving in a curved trajectory, we're going to use very basic names. We'll say that this u vector could in actual fact be replaced by two vectors. Now, I could call this an a vector, or I could say that it has a magnitude in the I direction, and that this is the one up the way, has b magnitude in the j direction. So let's look at what I mean. We have two little units now. I and j, and they're little vectors. It's a bit like measuring a table. You can't measure it and then go away and talk to somebody and explain to them how long it is unless you measure it according to a unit. You could say it's 1.5 meters. That means something to people. Just to say to them, well, I measured it and it's equal to 1 table length is irrelevant. It has no value because there's no unit. Here we're saying this u vector that's going off at an angle is being replaced by a horizontal vector which has a magnitude a, that's the length of it basically, and in the horizontal direction we've now defined this little I vector. We're also saying that there's a second component to u which is vertical, and it has magnitude b, which is the length of this vertical line, and its direction is defined by a unit vector called j. The good news here is by doing this, the infinite number of different sized horizontal vectors that you can have been replaced by one horizontal vector which is called I, a unit vector, and a magnitude. It's how much in that I direction. It makes life easy for us, okay? And you should be able to see that fairly quickly. So then, what do we know? Well, we know that gravity is going to be playing here. If you now think about it, if you have an object gravity operates straight down towards the center of the earth. So we will say gravity is going to pull in that direction. Now if you looked at that v vector, that u vector that we have, this one over here, we split it into a horizontal component, that guy, and a vertical component. Let's see if we can do the same thing with this gravity thing. Gravity is vertical. That means it does have a vertical bit, but it has no horizontal component because it is perfectly vertical. It's like the y-axis doesn't have an x component. So then, what we've learned from this is that once we've kicked the ball or fired the projectile, we will have a force acting on it, and the force acts vertically. It's a pulling down force, and it's due to gravity. But horizontally we don't. And while we're in a vacuum, there's going to be no external force acting on the object. So the interesting thing is, as we go across here, as we look across all the way along here in the horizontal direction, and we are just thinking of, oh, it's there, it's there, it's there, it's there, and you just follow it. At all times, the horizontal velocity remains the same. It stays as the initial velocity, ai. No change. So if you want to know how far it has moved horizontally, we'll say when time is t, well, the distance it'll have moved will just be a multiplied by t. After 3 seconds, it'll have moved 3a. After 15 seconds, assuming it's still in the air, it'll have moved 15a. That's very handy. Vertically, what's happening? Well, let's look at our basic equations. That is the first of the three equations of motion. And we're saying at a particular point in time, what will the velocity be on the vertical? Vertically, what we have is b was the original. Now, this thing here, I will change this, please. Allow me to change this to an f rather than an a. U plus ft, where f is the symbol being used for the acceleration here. So we're saying b. Now, the force from acceleration is going to be pulling down the way, so it's in the opposite direction to this little j vector up here. That means it's going to be minus, you'll have gt. Okay? So, yes, the vertical velocity is changing. A few little things that can come out of this. While we are looking at it going around in a curve, as you can see on the graph here, it's actually harder to think about it than to just say, and I'll draw a big dot down here and say, at any point in time, while it's going on the curve either up or down, there'll be a vertical bit to its motion and there'll be a horizontal bit to its motion. So then, going back up to the top drawing, you'd say, when it got to its top here, what happened? You will notice that if we drew a tangent here, and this is where your calculus comes in very handy, just by way of knowledge, we know that a tangent here is horizontal. Okay, and it has a slope equal to 0. That basically means that the vertical motion has stopped for a small little bit right there at the peak. No vertical motion. It means whatever vertical speed it has been eaten away by the gt. So under those circumstances, what you have is now at the peak, naught is equal to b minus gt. So we get a nice easy expression. The amount of time it took for gravity pulling on it to stop its vertical motion is equal to the vertical component of velocity divided by g. Scribbly writing, I'm sorry about that. What we're saying is the initial vertical component of velocity, which is this b thing here. Once I know that initial vertical component, if I just divide it by the value for gravity, I've actually found out how long it took for us to get to this location here, right at the top. Because the whole thing is symmetric, I now also know how long it takes for the thing to hit the ground over here. It's going to be twice that. So for it to get right to the very end, the total amount of time, which I'm going to show as a big T, is going to be equal to 2b over g. That's nice and easy. Now, what's the next thing we can say? The next thing we can say is horizontally, this thing has been moving at exactly the same speed, which is just a. So then I can say that the horizontal length that it got to, this big X over here, or R, or whatever you want to call it, is going to be 2b over g by a. I'll use a new screen just so as to clarify these last points. We're saying time to reach peak. That's the highest. The t was equal to b over g. Time of flight, which we can call t, is going to be twice that, 2b over g. We know the range now. And you call it anything you like. We can call it an x, or you could call it r, or you can call it anything. The range is the full length that it actually went from where it started to where it hits the ground. It's equal to the horizontal component of the original starting velocity multiplied by the amount of time it took. So it's equal to 2ab over g. Now, they're very interesting because they're really simple. What we need to know now is how high up did it go. And there are lots of little equations that we can use. Those three little basics, the important things about them is that even later on when we're starting to break down the velocity components by way of trigonometric values like u cos theta, u sin theta, etc., the same basic things still apply. So let's have a look. You just need to look at one more equation before we move on, and that was, it's the second one of the linear motion equations. So we're saying length, and in this case, if we're looking at the vertical part of it, we'll call it y. What is it equal to? Vertically, it was moving at b to begin with. You multiply that by how much time, and we're saying it's going to be minus, because g is going to be g is acting against the direction of motion. Now the nice thing about this is, even though it's a quadratic, see you have a power 2 here, you can actually break it like this. I prefer to break it like this because, especially for these flat surface problems, breaking it like this shows that you have got two factors and one of them will disappear very quickly for you. Okay. Okay. Now, how do you solve problems? If we start with the horizontal, we actually don't solve the problems because it'll keep going forever and ever because there's no force operating while we're in a vacuum. So to find out how far it goes, what you have to do is start looking at the vertical one. Now, what we do know about the vertical one is, to begin with, it's down at ground level, so the y is 0. And to end with, the y is 0. So in this equation here, if I set that equal to 0, I'll find out how much time that it took to fly the whole distance before it hits the ground. And what you will notice, when y is equal to 0, we have two factors already here. T is equal to 0. t is equal to 0 just at the start of the problem, okay? And the other is the b minus gt over 2 equals 0, which implies t is equal to 2b over g. Now you'll notice that we got to that up here by just appealing to the symmetry of the shape. So what does that basically mean? It means that, and by the way, this happens quite a lot in mathematics and in applied mathematics. If we can deduce certain characteristics about functions, for example that they're symmetric, we can actually bypass quite a lot of more tedious mathematics. We were able to deduce, once we'd worked out how long it took to get to the peak, we were able to deduce that twice that length of time would actually bring it back down to the ground again. Now, we've gone and proved it down here. We've looked at the two times where it's at y equal to 0, and one of them is right at the start, and the other one is at the exact same value of 2b over g that we worked out already. So then, let's just look at it, not all of the flight, we don't have enough room on the screen for it, but let's look at any given point in time. And we'll say, right at that point in time, we're looking at the particle. It's moving now. And what we have, the straight line, is tangential. Now, what we can say is that this here is the velocity. And we can call it the v vector here. This is the same thing we did down at the start. We looked at the u vector. And what we did back then was we drew a vertical line and we formed a right angle triangle. So let's do the same thing here. What do we know about this guy? We know that horizontally the velocity has not changed. So we just have an a in the I direction here. So the speed is a. Now, by the way, be clear in your mind that speed and velocity are not the same things. Speed is a scalar. It just says like 30 kilometers an hour. Velocity is a vector. It also has direction. Okay? So speed is the magnitude of the velocity. And velocity tells you, along with the magnitude, it tells you the direction. So in the horizontal we are saying that the speed is a, so the horizontal velocity component is ai. Vertically, we've already worked this out. Vertically we have in the j direction. You will notice that's just our basic little equation, the v equals u plus ft, where minus g is the acceleration. It's decelerating this item. So now we have a very nice situation where we can, at any point, no matter where it is along the curve, we can define the velocities of this thing. It's useful at this point because in the chapters they normally move on now to changing you away from this kind of, oh, it's A and B, horizontal and vertical, to a naming system that is more useful and that is also more common. And it's the one where we look at an angle. We say, what's the angle to the horizontal here? And the one he's used, the name he's using here is theta. So let's again look at how we can work out what components are. We've done this in the maths already, but it's no harm seeing it again. I'm redrawing the V. Okay, that length is V. If I want to know the two components in relation to V and the angle, the ways I always do it is I always imagine one unit. Which is just that far out. And we will go down vertically here. That's one unit. What we've managed to do when we do that is we've set up our unit circle. And you will see that in the first page of trigonometry in the logbooks. The unit circle is the starting point of all trigonometry. When I know that the radius I'm dealing with, this one unit, once I know it's one, I now have the names for two pieces. I have cos theta, which is out to there, and I know the vertical bit is sine theta. Now we can appeal to a junior cert theorem where we've similar triangles. They both share this angle here. The two of them have a right angle. That makes the top angles the same in each of them. So these are similar triangles. And we're saying, the hypotenuse in the small one is of unit 1, in the other one it's of unit V, so it's V times bigger. That means each of the other equivalent sides are V times bigger. So what we have over here is V sine theta, and that's in the J direction. And along here, that length is going to be V cos theta. So it's in the I direction. So we know how to break these things up. Now, from the little bit of work that we did on using A's and B's, we learnt a few things, and we learnt them very quickly. We learnt the amount of time it took to get to the peak. And it was simply the vertical component of the initial velocity divided by gravity. So let's look at that. We'll say right at the vertical one, the only difference over here in this first setup that we're looking at, this bit over here, as distinct from the V one, is we're calling it U instead of V. So let's look at that. And we'll say, so it was U cos theta and U sine theta. So we could say time to peak nice and easy. Time of flight I'll rewrite that. So those two we know already. What else do we know? We also know the range. If you remember, the full length that it would be moving at, it was, whether you want to call it x or whether you want to call it range, I don't mind. What did we get it to be? It was the initial horizontal velocity multiplied by how much time. We've already worked out how much time. It's this guy here. So what is the horizontal velocity when we're using cos's and sines? It's U cos theta is the initial horizontal velocity, and that doesn't change any way through, all the way through here. So what we have now is 2 interesting thing about that is if you know your trigonometry fairly well, you can replace this. We've actually moved a lot further in this book than I had thought. which is good for you to know. So then, in your logbook, you will find that that is going to be equal to an interesting question that can be asked now. What angle, initial angle, would give you the greatest range? Obviously, whatever energy was applied to the item, the U bit is not going to change here. We'll just say it was your ability to kick the ball is not going to change just because you're looking to check this problem. And gravity is not going to change. So the only thing that'll make a difference is sine 2 theta, and we want to get that to the max. The largest value that a sine or a cos can have is 1. So we would say for the max range, sine 2 theta is going to be equal to 1. That implies theta is 45 degrees. So if this was kicked originally at 45 degrees, you'll get the maximum range. And it also means, if this sine 2 theta becomes 1, that the maximum range is equal to u squared over g. These are extremely simple expressions. And what that means is that they're easy to remember. They're also very easy to work out. What we do then is we get little problems, and we generally apply these to them. One of the kind of problems that they actually ask you to do is something is projected. That's why it's called a projectile. And it says to you, oh, that it has to just pass an object. It has to just get over a particular object, okay? And one of the questions they'll often ask you is, why is it that there are two initial angles of projection that will get you to just go over this? We don't want to get an object going that far above it, and we certainly don't want an object to hit it. It's just get over this particular thing. There'll be a certain height here. Now, in that drawing there, it looks like we're right at the peak of the projectile's height. But, for example, we could have been asked an object over here, said, just get over that. The reason why you have two is because, now this might be a little hard for me to draw. Not the best. I'll try a little difference in it. If I fired it at that angle here, so that you've got to the peak before it actually just gets, before it gets over the object, that's the biggest angle that'll just have you go over the object. The other one is where it reaches the object, this black one, it reaches the object before it has reached the maximum. Now obviously the only time that the blue angle and the black angle there are the same is when the wall or building that you have to get over is exactly halfway along the flight path. In other words, you have got to the maximum height that the object can get to. In any other case where the object is placed along your horizontal line, you're in a situation where you have two possible angles. So that's the visual, or the reason why. So, and the working out of it is always easy. It's simply a matter of solving a particular little problem. Now, I just want to go back a little bit just to go through one of the problems that's in this particular book. And as I've mentioned to you, I normally use Conliffe's book. So if we had a particle and we know that its u velocity was 100 I, Now this is straight out of the book, okay? But what you should be able to see from it is that they're very straightforward problems. The reasoning is easy in them once you understand the basics, okay? Now there are 4 things being asked about. What's the time of flight? You should be able to work that out. The range of the projectile, how far will it go? The maximum height attained, and the speed of it after 2 seconds. Now that's the kind of interesting one, because that will show you the in-between kind of positions by the example of after 2 seconds, okay? So then we're saying whether you call this A equal to 100, or you could call it the U cos of the angle, I don't care. Whether you're calling the 49 B, or whether you're calling it U sine theta, I don't care. It's just they're a different system for looking at the exact same thing. So then, what's the time of flight? Remember we said y is equal to 0. It has made it all the way back down, back down, and hit the ground. So y is 0 on the horizontal. And we're saying, now that is equal to the t outside of the 49 minus so t is equal to nothing. That is a solution, but it isn't a valuable solution. We knew it was on the ground to begin with. However, for the sake of our mathematics, we have to keep it in the equation. It doesn't supply a lot of insight to us. The second one will. What we have is g by t over 2 will be 49, and in this case he's going to be using I think it's 9.8 for gravity. So what we get from it is that t will be 10 seconds. 10 seconds flight. So how far did this thing go? Range. Horizontal component of velocity didn't change at all. So it's going to be equal to the 100 by time of flight so it went a kilometre. Now what do we know? We also know that from the symmetry of these things, that half of the time of flight is how long it took to get to the peak. So we're talking about max height. What we will just do is we'll use half of the 10 seconds, and we will say, so y is equal to that many meters. So it actually got to a maximum of height of 122.5 meters. Now, just out of idle curiosity, and to see if I can find it quickly for you, there's a very interesting problem in the application of differential equations, because it's almost the same sort of thing as this, only it happens to be going just vertical. But the questions that are being asked, and by the way, in this problem, because we're using calculus, we have wind resistance or air resistance, and it is 0.05 times the velocity squared, and that's a typical kind of thing. As the velocity goes up, the resistance is going up with the square of it. So becomes very significant for high velocities, not significant really for low ones. The interesting thing is it's asking you in relation to something being projected like this, and it says find the maximum height that it reached, and that is with where air is taken into account. And then one of the things it asks is, if you ignored air resistance, how high would it get to? Now, when you ignore air resistance, the height for this problem, which is on page 322 and 323, the height it got to was 128, which is very near the height of the one we have here. But when air resistance was taken in, it got to 26.2 meters. So you see how big of a difference air resistance can make. It's one of the reasons why the shapes of cars have to be so aerodynamic, and any other thing that you want to project through the air, because air resistance is a big problem. It is as big a problem as the difference between 26.2 and 128. It's massive. Now, believe it or not, in the Conliffe book, the projectiles are split into two chapters. The first one has to do with horizontal planes. All the concepts for the horizontal planes, we've got through them. You can see how the problems work. They're straightforward. What I would like you guys to do is to go, and whether you're using this one or the Murphy book, I don't mind, apply a few of the problems. Just get to use them. This section stays very easy until we get to inclined planes. And in both books, inclined planes are seen to be a factor harder than this. But what you will find out the next day, because that's the next one we're going to talk about, that there's a shortcut or a trick that can be applied, a simple mathematical trick, which, by the way, you do use already in Leaving Cert Maths, and it will turn the projectiles on an inclined plane into something just as easy as this. Okay? Bye now.